Alright, so let's go ahead and almost finish out this section with another example. This will end our examples for the basic material. There's still one or two more tiny subtopics. Actually, one more tiny subtopic after this, but this example is going to be non-homogeneous, as you can tell, example, and we solve this using the same old methods that we would use if we were solving any ordinary differential equation of high order. We'd first solve the homogeneous version. So I'll write that down. I think I already have the right pen color, but we're going to solve the homogeneous version. X squared y double prime minus 2x y prime plus 2y is equal to 0. And this time I'm just going to jump right into the characteristic equation. So the characteristic equation is going to be m times m minus 1 minus 2 times m plus 2. So very quick, equals 0. And then distribute and collect, so that's m squared minus 3m plus 2 is equal to 0. And finally, factor. M minus 2, m minus 1 is equal to 0. So far, it's not a terribly difficult homogeneous equation to solve. We get the complementary function to be c1 x to the second power plus c2 x to the first. Perfect. And now we concern ourselves with solving this homogeneous piece, or non-homogeneous piece. And so the way we're going to do this is using variation of parameters. But big warning here, I'm going to scroll up or down a little bit and then put in a warning. Variation of parameters requires standard form. And remember when we derived the variation of parameters method, I had mentioned that variation of parameters works, excuse me, as long, even if you have non-constant coefficients. However, we did the proof using constant coefficients, but we can use variation of parameters even for this differential equation. But I'm going to go ahead and rewrite it in standard form. So divide everything by x squared, right? So you have 2 over x here, and you have a 2 over x squared here, and then you have an x squared e to the x there. Now, it turns out variation of parameters does not rely upon any of those coefficients, not this guy, nor that guy right there. They don't matter. What does matter is this. Remember, that is our g of x, and you will not know g of x until you place your differential equation into standard forms, into standard form, that is. And so now that it is, I will go ahead and write down all the information I have. I know that our first solution is x squared, our second solution is x, and g of x for us is going to be x squared e to the x. And now we can go ahead and jump into variation of parameters. And this is hugely important because when it comes time for an exam, it's a great question to ask. And it allows me to see in one single problem your variation of parameter skills, but also a Cauchy-Euler equation, how to solve Cauchy-Euler equation. So anyway, we know that we're going to find the Wronskian. The Wronskian is just y1 and y2 as the first row, and their derivatives as the second row. And then you take that determinant, that's x squared minus 2x squared, or a negative x squared. That's actually a very nice Wronskian. The first Wronskian, as always, you take that very same determinant, you keep the second row the same, but the first row is going to be replaced with all zeros except for the bottom element, which will be your g of x. And so here we have a negative x cubed e to the x. And finally, the second Wronskian. Again, second Wronskian, you get to copy the first row, x squared and 2x, but the second row will be that 0 in that g of x. And here we go. We just go ahead and take the determinant here. Whoops. X to the fourth e to the x. Great. And now I get to say that u sub 1 prime is going to be W1 over W, or the first Wronskian over the Wronskian. The first Wronskian being negative x cubed, e to the x, and the Wronskian itself being a negative x squared. So you can see that this is going to be x e to the x. And u sub 2 prime is the second Wronskian over the Wronskian itself. And again, second Wronskian is x to the fourth, e to the x. And the Wronskian is negative x squared, e to the x. Or negative x squared. So that's going to be a negative x squared, e to the x. And now we need to integrate both of those to find out what u1 and u2 are. Remember, just to remind you of what our goal is, I'll write this in here. Our goal is to find u1 and u2 so that our particular solution will be u1 times y1 plus u2 times y2. And the powerful part of using the Wronskians, or the variation of parameters method, is that it computes during the process all those unknown parameters that we would normally use when we do comparison of coefficients or undetermined coefficients methods. So anywho, let's go ahead and integrate both sides of u sub 1 prime. Let me get the right pen color back. So u1 is going to be the integral of x e to the x dx. And that is actually just going to be x e to the x minus e to the x. And that is one that I happen to know just because when you do any type of integration for a long period of time, that specific one creeps up a lot, the x e to the x. Essentially, let me use a different color here so that I can showcase this. I let u equal x, du therefore was dx, and I let dv equal e to the x dx, and therefore v itself was e to the x. And this is always equal to uv minus v, the integral v du. So if you look at uv, that's x e to the x minus the integral of v du. So that's the integral of e to the x dx, and you're subtracting that. So that's where we get that from. Okay, and then u sub 2 is not one that I have memorized, so we're going to actually have to go through and do u sub 2 here. U sub 2, I'll give myself some space, is equal to the integral of x squared e to the x dx. This is just going to be 2 integration by parts, actually. So I'll stick the blue for this. U is going to be x squared, so du is going to be 2x dx. And dv is e to the x dx, so therefore v itself, if you take the antiderivative, is e to the x. This is going to be uv minus the integral of v du, or in other words, getting my pen colors back, x squared e to the x minus the integral of 2x e to the x dx, or in other words, x squared e to the x minus twice the integral of x e to the x, but we just have done that one. That's going to be x e to the x minus e to the x, and you can now distribute. And remember, we don't worry about the constants. You might be wondering what happened to the constants of integration. I don't worry about those in this method because, sorry, I'm writing and talking at the same time here. I don't worry about that in this method because those constants are only going to regenerate the complementary function. So I don't worry about it in this process. Anyhow, so we get down to that the particular solution to our non-homogeneous is going to be u1, y1 plus u2, y2. So take that u1 that we have right here, and we're going to multiply it by y1, which is somewhere up here, x squared. So we're going to take x squared, we're going to multiply it by that x e to the x minus e to the x. So let's go ahead and do that. So that'll be x squared times x e to the x, that's x cubed e to the x, and x squared times that negative e to the x is just x squared times that negative e to the x. Then we're going to take, so that's u1, y1, and then we're going to take U2, which I'll highlight in a different color here, maybe this annoying blue. So U2 is this guy right here. And we're going to multiply that by Y2, which is this guy. We're basically going to tack on a power of x to that stuff in blue. So here we go. One last time. Tacking on powers of x's here. That's a plus x cubed e to the x minus 2x squared e to the x plus 2x e to the x. Now, you notice that in this process, you're going to have to combine like terms. That's very common. So at the very end here, we get 2 of those x cubes e to the x's, a minus 3 of those x squareds e to the x's, and then a plus 2x e to the x. Let me just look through and make sure that I added and did everything correctly. I did. Okay. So that's y sub p. We know y sub 1, or I'm sorry, y sub c was that constant times x squared plus a constant times x. So our full solution, y of x, is equal to c1x squared plus c2x plus 2x cubed e to the x minus 3x squared e to the x plus 2x e to the x. And technically speaking, I suppose you could factor out an x e to the x out of each of those, and you might have something that's factorable. However, when you go to plug that into a differential equation, you'll want to multiply that stuff back out. So it's probably easier just to leave it like this. But this is, right here, the solution to our original non-homogeneous Cauchy-Euler differential equation. Let me just show you that guy right there. So pretty nice. We actually are now at a point in this course where we're solving some fairly challenging differential equations. But what we'll have coming up in Chapter 6 will kind of be quite a bit more challenging. But at least at this point, you have all the tools you need to solve anything you can solve cleanly by hand without using something like a Laplace transform or a power series.